In this video, we're going to learn how to define the derivative using derivative notation. Previously, we learned how to compute the instantaneous rate of change of the function f of x at a particular point x equals a. To recap, the way we do this is as follows. F prime of a, meaning the instantaneous rate of change of f at the point a, is equal to the limit as h approaches 0 of the function f evaluated at the point a plus h, then minus f of a, all divided by h. But now we're going to learn how to compute f prime of x, the instantaneous rate of change of the function f of x for any general point x. This function, f prime of x, is called the derivative of f with respect to x. And the way we compute it is we just carry x through the same computations that we'd usually do. We just use x instead of a. So f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h. So this right here is our grand formula to compute f prime of x, which is called the derivative of f with respect to x. Alright, let's apply this concept to a concrete problem. We want to compute the derivative of this function f of x equals x squared. And then once we have the derivative, we'll use it to compute f prime of 0, f prime of 1, and f prime of 2. So all we have to do is use this formula. So f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Now we're told that the function is f of x equals x squared, so we can evaluate these f's in the numerator using that rule. So this is the limit as h approaches 0 of x plus h squared minus x squared all over h. Now we just simplify. So this x plus h squared in the numerator, we can expand that out to x squared plus 2xh plus h squared, and then we've still got our minus x squared. That's all over h. And notice that this x squared and this minus x squared cancel. So this is really just the limit as h approaches 0 of the remaining terms, 2xh plus h squared over h. And hey, each of these terms has an h in it, so we can go ahead and divide by h very cleanly. This limit as h approaches 0 of, well, 2xh divided by h, that just gets rid of the h, so we just have 2x, and then h squared divided by h, that gets rid of one of the h's in this h squared, and we still have one h left over, so just plus h. And we're taking the limit of that entire expression. Now we can go ahead and just plug in h is 0, and then we get 2x plus 0, so just 2x. So there we go, there is our derivative. F prime of x is equal to 2x. Now we'll go ahead and use that derivative to compute f prime of 0, f prime of 1, and f prime of 2. So that derivative function here tells us what the instantaneous rate of change is at any general point x. So we can compute f prime of 0, f prime of 1, and f prime of 2 by just plugging in these values for x. F prime of 0 is just 2 times 0, which is 0. F prime of 1 is just 2 times 1, which is 2. F prime of 2 is just 2 times 2, which is 4. So there we go. There is f prime of 0, f prime of 1, f prime of 2, and this really demonstrates the beauty of the derivative. What's so useful about the derivative function is that we can just perform a single computation up front. compute this limit up front, and then whenever we want to compute the derivative at a point, we can just plug our point into this function, rather than doing this whole big computation all over again. Now that we know what the derivative is, let's talk a bit about what notations can be used to represent it. So there are several different types of notations for the derivative of a curve y equals f of x, and they all mean the same thing. First of all, there's the notation that we're already familiar with, f prime of x. Sometimes, though, they'll drop the x and you'll just see f prime. Another notation, given that the curve is y equals f of x, is to write y prime of x. In this notation, we're interpreting y itself as a function of x, where the function is given by f of x. And likewise, you might see the x removed also, so that would just be y prime. Alright, so these notations here are pretty similar to what we already know. They all use prime notation. But there's also another type of notation, Leibniz notation, which looks a bit different, but really just means the exact same thing. Here's what these notations look like. First of all, there's df over dx, and second of all, there's dy over dx. Now, this notation might look kind of clunky, but it's actually quite intuitive regarding a physical interpretation of the derivative. We can think of dy dx as representing a very, very small change in y divided by a very, very small change in x. In other words, an instantaneous rate of change. And the instantaneous rate of change, of course, well, that's just the derivative. So the big takeaway is, no matter what kind of notation you see in a problem, if you see any of these types of notation, they're all referring to the same thing, the derivative. Here's another problem for us. We're given this curve y equals x cubed, and we want to compute y prime of x. Remember, y prime of x is just another notation for the derivative. So really, we just want to differentiate x cubed. So let's write that down. Y prime of x is the derivative of this function y equals x cubed, and let's just go ahead and write down the limit as h approaches 0 of y of x plus h minus y of x all over h. So we just have to compute this limit using the function definition y equals x cubed. So let's go ahead and stick that in. Limit as h approaches 0, y is just x cubed, so y of x plus h is just x plus h cubed. Same idea, y of x is just x cubed. That's all over h. To multiply out this x plus h cubed quickly, we'll just use binomial expansion. If you need a refresher on that, I encourage you to take a look at the binomial theorem. And you can always double check by actually multiplying out x plus h times x plus h times x plus h and verifying that it comes out to the same result, x cubed plus 3x squared h plus 3x h squared plus h cubed. But as you see, the binomial expansion method is a lot faster than multiplying it out the long way. So it's very useful when computing derivatives. Alright, so we've expanded out this numerator, and we see immediately that this x cubed cancels with this minus x cubed. Now the remaining terms all have at least a single copy of h in them, so we can go ahead and divide all of those by h, the denominator, and clear up that fraction. So this is limit as h approaches 0, divide each of these terms by this h in the denominator, and we just get 3x squared plus 3xh plus h squared. And we're taking the limit of that entire expression as h approaches 0, so we can just go ahead and sub in 0 for h here. So 3x squared plus 3x times 0 plus 0 squared. And 0 squared is, of course, 0, so we can forget about it. 3x times 0 is, of course, 0, so we can forget about that. And all that's left is 3x squared. So that is our expression for the derivative. Y prime of x is equal to 3x squared. Here's another derivative problem for us to try. So we're given this curve y equals 1 over x, and we want to compute dy dx. And of course dy dx is just the derivative. So we can just do the same procedure as usual. dy dx is just the limit as h approaches 0 of y of x plus h minus y of x all over h. And we can use our function definition for y of x. Y of x is just 1 over x. So we'll go ahead and plug that into our limit problem here. So y of x plus h is then just 1 over x plus h. And then y of x is just 1 over x. And that's all over h. Okay, so this is looking kind of messy now, but let's try and clean it up a bit. Instead of saying all over h, let's just interpret that all over h as multiplication by 1 over h. So 1 over h times 1 over x plus h minus 1 over x. It means the same thing, but it's just a lot nicer to look at. Alright, so now let's go ahead and think about combining these two fractions. In order to combine fractions, remember, they have to have a common denominator. So first of all, we want to rewrite these fractions so that they have a common denominator. Common denominator is just the least common multiple of x plus h and x. And well, these denominators don't have any common factors, so we can just think about multiplying them together. So x times x plus h will be our common denominator. So we want x times x plus h, and then minus something over x times x plus h. But we also need to make sure that these fractions are equivalent to the original ones. So we need to make sure we're multiplying by the same thing on the numerator and the denominator in each particular fraction. So for this first fraction, 1 over x plus h, the denominator is being multiplied by x. So that's what we need to do to the numerator also. 1 times x makes x. Same idea for this 1 over x fraction, but the denominator this time is being multiplied by x plus h. That's the new term that is in the denominator. So we also have to multiply the numerator by that. So 1 times x plus h. Now we can go ahead and subtract these fractions because they have the same denominator. So limit as h approaches 0 of 1 over h times, so we'll put this all over a single denominator, x times x plus h. And then we've got x, the numerator of this fraction, then minus the numerator of the other fraction. Remember to use your parentheses. We're going to have to actually distribute that negative sign. So let's go ahead and do that. Distribute the negative side, and we get the following. 1 over h times x minus h in the numerator, then over x times x plus h. Alright, so immediately we see that x minus x, that cancels out. And then all that's left in the numerator is this negative h. But we're multiplying by 1 over h. So this 1 over h will cancel with that negative h, and we've just got negative 1 left in the numerator. So this is the limit as h approaches 0 of negative 1 over x times x plus h. And we can go ahead and just sub in h equals 0. Let's do that, and we get negative 1 over x times x plus 0. And x plus 0 is, of course, just x, so this is really just negative 1 over x times x, which is just negative 1 over x squared. So that's our equation for dy dx. Just negative 1 over x squared. So now we know how to define the derivative using derivative notation. And in the future, we'll learn several rules that we can use to compute the derivative quickly without having to compute this big limit process each time.